In this video, we are going to talk about the system schema, and I am going to talk again about conservation of mechanical energy and the work energy theorem. I realized that I've talked about these two topics before, but I felt that I didn't really do a good job of discussing these topics, so I'm going to do it again, and this time I hope that my discussion is much better. Okay, so in any physics problem, the first thing that you need to do is to define your system. So what is a system? Well, I'm going to talk about what a system is later, but basically it is just your object or the group of objects that you are studying. And you have to be clear about that. When you're reading a problem, you have to know what your focus is. So what is a system? It is just a portion in the universe that has been chosen for studying the changes that take place within it in response to varying conditions. You read a problem, and sometimes it's very easy to figure out what your main object is. Like, for example, if the problem is about a car that is moving at 5 meters per second, then it seems pretty obvious that your main object is the car. But sometimes you can actually manipulate the problem so that you're choosing a system to not only include the car but also the objects around the car. And if you do that, that actually makes solving the problem easier because then you can utilize something, a principle in physics. You can use that because of the system you chose. I know it's pretty vague, but I'm gonna elaborate further when we talk about the system schema. So a system schema is a way of being able to define your system. So a system schema consists of identifying and labeling all objects of interest from a given physical situation, as well as all the different types of interactions between the objects. You do this before you create the free body diagram. So if you read a problem, maybe the problem will provide you with a pictorial representation, like a picture that accompanies a problem. That's good, but before you dive right into the equations, you need to first create a system schema so that this diagram will help you visualize what you really need to see, not just the objects, but the forces between those objects. And once you have that, it is now easier for you to create a free body diagram, which is a diagram that lists all the forces and the directions of the forces of the main object or the main system that you are dealing with. After creating the system schema and the free body diagram, that's the time that you create or list down the equations that you need, and that makes for a very organized way of solving problems. And really, it just makes your life easier. Let's look at the following system schema examples. For example, I give you a problem involving an object that lies motionless, just like this box and the floor. Now, if you look at that, this is actually a pictorial representation. But in solving a physics problem, a pictorial representation is not enough because it hides some very important principles and physics concepts. In order to reveal those principles and concepts, you have to draw a system schema first. Now, this diagram right here is the free body diagram, but before you are able to do this, you have to have a system schema. So before we can create a system schema, we need to figure out what the objects are in our pictorial representation. Of course, there is a box, and then there is a floor, and wherever there is gravity, you have to include the Earth as one of the objects. And What are the forces involved? Well, there must be a normal force and a gravitational force. But let's see what that system schema looks like. Oh, there it is. Now I want you to take your time in your notes to really copy this, because this is very important. The words encircled are the main objects in your problem. For example, you have the box, the floor, and the earth. And these double arrows between objects, they are the kinds of interactions or forces between the objects. You know, force is always between two objects, and it seems pretty clear from the problem or the pictorial representation that there is a force between the box and the floor because there is an interaction between the box and the floor, and that interaction is called the normal force. And there is also an interaction between the floor and the earth, and that is known as the gravitational force. All these objects, the box and the floor, they are all attracted to the earth, otherwise we'd be flying out of space. Now is your chance to define what your system is. And in this case, I have defined the system as just composed of one object, and that object is the box. I do that by creating dashed lines around the object or group of objects that I want to be a part of my system. But for this particular situation, I wanted to focus on the box. That's why my dashed line is just around the box. And by drawing a dashed line, you not only point out what your main object is, but what the external or the internal forces are acting on that system. You would know that a force is internal if that force is within the dashed line. You would know it's an external force acting on the system if only part of the force is inside the dashed line. As you can see here, only part of the normal force is inside the dashed lines, and only part of the gravitational force is inside the dashed line. Therefore, the normal force and the gravitational force, these are the external forces acting on our system. And by figuring that out, you can now create a free body diagram, which all actually lists down all the external forces acting on your system. And your system in a free body diagram is reduced to this small dot in the middle. And these two forces are the external forces acting on your system. And not only does the free body diagram show the forces, they also show the direction of these external forces. The normal force points upward because it is always perpendicular to the surface as well as supporting the box from falling down. And the gravitational force is always pointing towards the center of the earth, and that is, in this case, downwards. Okay, let's look at another system schema example. An object is suspended from the ceiling. You have the ceiling right here, the rope, the box, and the earth. But normally, for physics problems like this, the rope is massless or has negligible mass. So it doesn't really play a part in being one of the main objects. But what the rope does, however, it is that it provides tension to whatever it is supporting. So this is what the system schema looks like for this particular pictorial representation. And then it has the ceiling as one of the main objects, the box as one of the main objects, and of course the earth because we are in planet Earth. The ceiling and the box are connected by a rope which produces the tension force because whenever there is a rope that is taut, T-A-U-T, then it is providing force somewhere, and that force is called tension force. Of course, all of these objects are under the influence of Earth's gravitational force. Therefore, we create these double arrows, all pointing to the objects. Okay. Now, it's our time now to choose the system. And if you remember from the previous slide, we choose our system by drawing a dashed line. And in this case, I just choose the box. And I hope you see that there are no internal forces in our system. Maybe there are microscopic ones, but not really from a macroscopic perspective. But there are external forces. These are the tension force because they are only partially inside the dashed line and the gravitational force. So when we now create our free body diagram, we now know to draw two force vectors that are externally acting on our system or object. These are the tension force and gravitational force. And that's what we do. We know that tension force is pointing upwards because it's supporting the weight of the object, which is Fg, pointing downwards. Let's look at another example. The object is pulled by a force parallel to the surface. Now, something is obviously pulling on the box. Maybe it's a person, so we might include that as one of our main objects. Of course, our box is also one of the main objects. The floor is one of the main objects, and the earth is an object that will never go away if we are dealing with objects that are on earth. So let's see. I failed to mention that the box and the floor is frictionless. So there's that. But anyway, here's what the system schema looks like. Take time to, maybe you can pause the video so you can draw this system schema. I just put a question mark here because I don't really know who's or what's applying this pulling force, but it doesn't really matter. You can see the box in the floor, normal force, floor in the earth, gravitational force, also earth in the box, gravitational force. And I guess I forgot another, so maybe I'll just draw. There's gravitational force here as well. Whatever that is. I'm willing to bet that's a teacher, a physics teacher. So we can also write just teacher. And perhaps the teacher is also interacting with the floor if it's standing on the floor. If she's or he's standing on the floor. That would be another normal force. But can you guess what our system is? What we are focusing on? You're right, it's the box. So we draw our dashed lines around the box. And we see that there are no internal forces, but there are three internal forces. That pulling force, the normal force, and the gravitational force. And so we draw our free body diagram as follows. Pretty easy, right? This is probably the last example for system schemas. The ball is at the top of a parabolic trajectory. Here it is. Right. So surprisingly, there's only one force acting on the ball, and that is gravitational force. Okay. Well, that's not really a surprise. But as you can see, our problem has only two important objects, the ball and the earth. We're assuming that there is no air resistance here. Otherwise, the air would be one of the main objects as well. But if there is no air resistance, then it's just the ball and the earth interacting gravitationally. And we see that as we highlight and make the ball our system, we have one external force, and that is the gravitational force. Now, I want to do something different here. What if I choose the system to be consisting of both the ball and the earth? Because I can do that, right? Now, what happens to the gravitational force? Will it still be an external force? No, it's not an external force anymore. In fact, it's an internal force. So if you draw the free body diagram, you can't draw, you don't draw anything at all. There's no external force here. So that's what your free body diagram looks like. However, there's something special about this, and it's called the conservation of mechanical energy, which I am going to share in the next slide. Because according to the conservation of mechanical energy, if you have a system that only has internal forces and no external forces, and if that internal force is a conservative force, and a conservative force is either gravitational force, just like this example, or electric force, which is actually our main topic for grade 10 physics, and also spring force. So these are the three forces that are known as um, conservative forces. And if you have a system that is made up of internal forces that are conservative forces, then you can use the conservation of mechanical energy. You can use that concept to solve problems, and that involves kinetic energies and potential energies, and the mechanical energy being conserved. We'll look into that more in the next slide. As I mentioned, there are no external forces, and in here, gravitational force is an internal force. So here's what I'm talking about. Let's just focus on the top. These are the two important things that you need to remember while solving problems involving energy. So this is really important, the work-energy theorem. And all of this has to do with defining your system. So here it is. Sorry. The work done by the sum of all external forces acting on an object or system equals the change in its kinetic energy. So if you have an object, right, let's say a ball, and there is an external force acting on the ball, yeah, like that. Let's say there's only one external force acting on the ball. And now, do you remember Newton's second law of motion? F equals ma, right? So since there's only one force acting on the ball, this force will cause that object to accelerate. And acceleration leads to change in velocity, which in turn leads to change in kinetic energy. Why? Because kinetic energy is a function that includes velocity, 1 of mv squared. So if your velocity changes, since it is directly proportional to since kinetic energy is directly proportional to the square of velocity, they are related. If v increases or changes, ke also changes. So that's the simple proof for why this thing works. This equation you can use if the way you define your system reveals that there are external forces acting on the system. However, let's look at the other tool. This time, when you have a system that doesn't have external forces. The total mechanical energy in a system, i.e. the sum of potential plus kinetic energies, it remains constant as long as the only internal forces acting are conservative forces and there are no external forces. Right. Now, if you clearly define your system so that no external force is acting on it, then you can say this one. I really like the second one. Delta KE plus delta PE equals 0. Why do I like that? Because it makes a lot of sense. If you have a system and only conservative forces are acting internally, then mechanical energy is conserved. That means if within your system all of a sudden one object had a plus 5 increase in kinetic energy after some time, which implies that it has gotten faster and maybe it gained speed. Now that is suspicious because if that's the only thing that happens in your system, just all of a sudden the object in your system gained speed, then that means it created energy for itself. But energy cannot be created. It can only be transformed from one form into another. I'm sure you've heard that. So there's got to be some compensation somewhere. And true enough, that potential energy of that object actually reduced by the same amount of energy that it gained kinetically. So it gains speed, but at the expense of maybe losing some stored potential energy. It loses speed, but perhaps if it gained potential energy. So that's how conservation of mechanical energy works. Energy cannot be created nor destroyed. So it cannot all of a sudden get faster without some form of compensation in the form of change in potential energy. Now, this is wrong. Oh, I am so sorry. This other formula, this has to be NC or non-conservative forces. I'm going to edit this later, but I'm glad I can do this with. Now, what's the difference between the left equations and the right equations? Now, if you have a system and there are, of course, internal forces, there are conservative forces like the force of gravity. What if there's another internal force somewhere, but it's not conservative? It's not force of gravity. It's not electric force. It's not spring force. But there's another force, and it happens to be internal as well. How will that fit in your equation? Well, it fits in this manner. Like now, I really like the second one as well, and I think it's intuitive. So it's not zero, right? So if you gain speed 5 joules, since Ke plus P is not zero here, delta Ke plus delta P equals not zero, then perhaps maybe the potential energy just reduced by 4 joules. So there's extra 1 joule. And that actually goes to the work done by that non-conservative force. So that's what happens sometimes. For example, is friction. When something slides down a friction-full ramp, and maybe that frictional force will do work internally, and that may use some of that initial energy and convert that initial energy into heat. So some of that energy is lost because of the non-conservative force acting on that system. Nevertheless, in the most problems that we will be dealing with, because we are going to talk about electric force and electric potential energies and constant electric fields, there will be no non-conservative forces basically. So this two sets of equations on the left side, these are the most important ones that we will be dealing with and you need to remember. memorize, but not really memorize, just familiarize and master. Okay, here are your two best tools for solving energy-related problems. Work net is equal to change in kinetic energy, and change in kinetic energy plus change in potential energy is 0. You use the first equation, equation A, if there are external forces acting in your system. You use letter B if there are only internal forces in your system and they are conservative forces. Okay, let's look at some examples. A 5-kilogram apple starts from rest and falls 3 meters downwards. What is the final velocity of the apple? You can actually solve this using kinematic equations, free fall kinematics, but we're going to do this right now with energy. So this is the system schema of the problem. You have a ball and an earth. And that's all. Those are the only two objects you have in this problem. There is no air resistance, and they are interacting gravitationally. The ball is interacting with the earth, and the earth is acting on the ball gravitationally. So let's focus on the ball as our system, right? Are there any external forces? Yes. And since there are external forces, we are going to use letter A. Work net is equal to change in kinetic energy. It's called work net because it's the sum of all the work done by all the forces acting on the object. All the external forces. All the work done, the sum of all the work done by all the external forces acting on our system. Fortunately, in this problem, there's only one external force, and so our gravitational force, that is. So our work net is equal to change in KE becomes just FD cosine phi is equal to delta KE. That's actually just the formula for work, if you remember, where here phi is the short angle between F and D. So we need to figure out what that angle is. Now, what is the direction of the apple's displacement? It's downward, right? So you have a downward displacement vector, and the gravitational force is also downward. And whenever you have F and D pointing in the same direction, whether left, left, right, right, up, up, down, down, to a certain angle, as long as they are in the same direction, you use 0, right? FGD cosine 0 degrees. And here, delta KE, we expanded it because KE is 1/2 mv squared. So final minus initial. And our force is, again, FG. So FGD cosine 0. Cosine 0 is 1, so that simplifies. And FG is mg, just the weight of the object. So it becomes mgd equals 1/2 mvf squared. Notice that there is m both sides of the equation. You can cancel it out. Gd is equal to 1/2 vf squared, and further manipulation gives you vf is equal to square root of 2gd, and substituting g and d, notice that the mass of the apple didn't really matter. You get 7.7667 meters. There's another way to solve this problem. Let's drink water. And one way to solve this problem, another way to solve this problem is if you treat your system to be both the ball and the earth. Now, are there any external forces in this system? No, there are not. There are none. There are only internal forces. And what's more, the internal forces is just the gravitational force. It's a conservative force. And because it's an internal and conservative force, we can use equation B, which I will just show here. And as you can see, the free body diagram is just a black dot. Delta KE plus delta PE equals 0. Okay? Don't forget, you can use this equation if you're dealing with a system with no external forces, only internal forces. And this internal force is a conservative force, like gravity or electric force. Okay. Now you do have to remember what the formula is for gravitational potential energy. And gravitational potential energy is mgh. And you have to be very sensitive when you use this formula. You have to define your HI and what you want to call that and base everything off of that. And in my case, my HI is here. You can really choose, you can really just choose, it's arbitrary where you want HI to be. You can even put HI where the apple is 3 meters down. But for me, it makes sense to make HI equal 0 at the starting point. And so here, you have an HF. It's at the 3-meter mark, and I'm gonna say it's negative 3 meters because it's down the 0, below the 0. And I just define any downward motion to be negative. You can even choose to make any downward motion positive. It's up to you as long as you're consistent. But for me, it makes sense to make downward direction negative because I'm just used to doing it like that. Okay, let's proceed. So as I mentioned, I arbitrarily defined where my HI equals 0 is. And in this problem, I chose it to be the starting point of the apple. What happened here? Cancel ang 1/2 mvi squared because the apple started from rest. Cancel ang mghi because hi equals 0. So we are left with these two simple expressions. And we basically get almost the same formula as the previous. There's just this negative sign here inside the square root. Don't worry about that because remember our h is negative. H final is negative 3. So those negatives will turn into positive. So we don't have to deal with imaginary numbers. We also get the same answer, 7.67 meters per second squared. Meters per second. Okay, so defining your system matters. Here's an example, but I didn't really put any numbers. On roller coaster problems with no friction and no air resistance. Here is our system schema for that. We have the roller coaster, we have the track, and the earth. So you can see the roller coaster and the track, they interact with the normal force. And both roller coaster and track are attracted gravitationally to the earth. Let's focus on just everything, right? Because we can do that. We include everything in our system, even the earth. The earth, the roller coaster, and the track. So that's what our free body diagram looks like. There are no external forces. But let's look at our internal forces. And what do we see? Do we see any conservative forces? Yes, we do. We see gravitational force. That is a conservative force. And therefore, we can think about changes in potential energy, in particular, gravitational potential energy. But we do have a non-conservative force, and that is the normal force. So instead of using delta KE plus delta PE equals 0, we have to use this formula. Delta KE plus delta PE equals the work done by the non-conservative force. so that if delta KE and delta P don't add up to 0, then we know that that extra excess or lack of energy that went to the work done by the non-conservative force. Maybe that non-conservative force used it to heat up, converted some of that energy into heat energy, and at least we can account for it. But the good thing about the normal force acting on the roller coaster is that cosine 90 is always 0. Cosine 90 is the angle between the roller coaster and the track. It's always 90. Let me just illustrate that. If the roller coaster is here, normal force, which is always perpendicular to the surface, is also perpendicular to the direction of the roller coaster's displacement or distance traveled. Even if the roller coaster is right here, the normal force is in that direction and the displacement is in that direction. So they're always 90 degrees. Everywhere around, everywhere in this track, the angle is always 90 degrees. And the great thing about cosine 90 is 0. So we still go back to as if the track didn't produce any non-conservative forces. As if there are no conservative forces. There are no non-conservative forces, only conservative forces. Well, we know that's not true. There's normal force and non-conservative force, but apparently it doesn't contribute to any work. So, how about this? A charged object Q equals 2 microcoulombs starts from rest and accelerates downward due to the constant electric force acting on it. The plates are 5 millimeters apart. The plates create a constant electric field of E equals 1,500 newtons per coulomb south. Again, in this setup, the electric field is constant between the plates. So this positive charge will experience an electric field pointing downwards. And since it is a positive charge, and remember F equals QE, right? Since this charged object is positive, it will also experience a force, electric force, pointing in the same direction as the electric field. Okay, let's draw the system schema for this. Actually, the system schema is just composed of the charged object, this little blue circle, and the metal plates. And actually, the metal plates and the charge object, they interact with the electric force. So that's a very easy system or system schema. So let's define our system to be just the charged object. So our free body diagram will look like that, with the electric force pointing downwards since our charged object, our test charge, is positive. Okay, we can use this equation, right? Because there is an external force acting on our system. Indeed, because of the electric force and because force is equal to mass times acceleration, and acceleration changes velocity, and change in velocity results to change in kinetic energy. In other words, this object will gain speed as it goes down towards the negative plate. It will get faster and faster. It will gain energy as a result of the work done on it by an external force, which is the electric force. Okay, FD cosine phi is the formula for work. And our F is QE because that's just the formula for electric force on a test charge exposed to an electric field. Our theta or our phi is 0 because the displacement is downward and the force is also downward. And you can use that formula. Actually, I didn't really ask for anything, so maybe you can ask for what the final velocity is. You can use that formula. But this is basically all the steps you need, and then you just find a way to isolate which variable you want to get the value for. So this is the last slide, and you might be wondering what this box is, but I'll make it clear for you right now. Okay, if we chose our system to be only the charged object, then we can use that first equation, W net is equal to delta KE, and we just call the work done by the electric force or the electric field is equal to the change in the kinetic energy of the object experiencing that force. What if we choose both the charged object and the metal plates to be our system? That means that we have no external forces, but we do have one internal force, and that is the electric force. And as I mentioned earlier, the electric force is a conservative force. Therefore, we can use the second formula. Delta KE, remember, plus delta EPE. Take note that I chose EPE as our symbol for electric potential energy. You can also use, I'm going to share UELEC if you want. I used to do this, but I think now I don't want to use that anymore because it involves too many letters. Delta EPE is fine. There is question, na by gravitational force? Nah, but in this case it's negligible because the charged object is very small mass. It's a point charge. Manipulating that previous equation, we have delta KE is equal to negative change in EPE. We can actually combine. See, both equations have delta KE. And this is, I put it in a box because it's one of the most important equations in electrostatics and electric physics. Here, that the work done by the electric force is just a change equal to the negative change in the electric potential energy of the charge. In other words, if you want to calculate how much charged objects gain from moving from one plate to the other or lose, then you just calculate the work done, and apparently you multiply it by a negative sign. This formula is important because it allows us to calculate changes in energies, and by calculating how much energy charged objects gain, we can create devices that can store energy and figure out how much they can store and how much energy they can release. I'm talking about capacitors or batteries, and so I want you to take your time to appreciate the two equations in the box. And time's up, and that ends my very long video, perhaps the longest in my channel.